Welcome to another exciting computer architecture class. We just got done with our midterm, and I just wondered if there were any questions left over from the midterm. Yes, somebody said privately. What is the question? You want to type it privately, and I can go over it privately with the class, which is not exactly privately, but I won't mention your name if you type it. Never mind, that was from before with the clock. Oh, sorry. So the let's see. Last time we did the a little bit of a review for the homework due next Thursday. Did anybody have any questions left over from that review? So this is a homework due Monday, Tuesday, Wednesday, Thursday, perhaps in 4 days, 3 and a fraction days. So if there's no questions there, what I would do is cover this material I have prepared here for network programming. And for whatever reason, this doesn't show up in full screen. I don't know why. Slideshow, setup show, something about slideshow primary monitor. Why isn't it in full screen? Well, life in the big city. What are you going to do? So this is a review of some of the stuff we've seen before about the International Standards Organization's OSI model. This is the one that has 7 layers associated with it. What we're kind of interested in doing is seeing how this relates to computer architecture, specifically distributed computing, what the differences between so-called cluster computing and grid computing is. Some people have suggested that grid computing or cluster computing could be used for doing things like Bitcoin mining, which is certainly true. Others have suggested that they create new systems like Hadoop, which is a grid computing system, or Boink, which is cluster computing. Sorry, go ahead. So at some level, these directly impact our view of how computer architectures are created. We're used to seeing all kinds of interesting distributed computing servers. So you'll have perhaps a printer that goes on the network, and it's a print server. It's got a built-in network appliance. You plug it into the network, and it just comes up as available in your so-called network neighborhood. Other services include mail and Echo and SSH and Telnet, FTP, file services. These are all services that we're used to having on a network, and so we're actually engaged in taking distributed computing kind of for granted because we're always getting these kinds of services. Domain name service, DNS, the dynamic host control protocol, DHCP, all these different interesting and wonderful services we take for granted. And oftentimes they lead to zero administration overhead networking, such as DHCP, which lets us get an automatically assigned Internet Protocol address. So there is this idea that somehow these distributed computing systems can be brought together and turned into a single virtual computer. And in that case, you've created what's called a cluster. And what the cluster does is it attempts to take a group of computers and treat them as a single system. And so this is a little bit different than having a distributed computing system where you say, well, this computer does your file services and that computer does your print services. Here we have a whole bunch of computers that are tied together and treated as a parallel virtual machine. And Beowulf clusters were sort of the first example of that, done in NASA in the early 90s. There's many different interesting and wonderful examples of software that enables us to do this tightly clustered computing architecture. And being able to work in a regional data center and setting up the computers so that they all interact closely with one another and interdepend on one another to create a single virtual machine is something that people are kind of interested in doing in places like in the cloud. So, for example, Amazon regional data centers, Oracle has regional data centers, IBM is doing cloud computing. If you had very few resources and all you had was a bunch of Raspberry Pis, like you see here, you could create your own little cluster and run it in your dorm room or whatever you like. And this is sort of fancy, actually. You don't really need the little brass standoffs and the laser cut plexiglass doodads, but doesn't that make it nice? I mean, really. And of course, you've got the ability to extend this, right? I mean, I guess the sky's the limit. You can keep going with that stuff. And then in principle, you'd have to power it and throw on a network and do all this other stuff. But you don't actually have a keyboard and a mouse on every single machine because they'll all be participating into the same cluster. And there's kind of a miniature virtual supercomputer in the creation here. You don't need to go out and buy expensive workstations. So that's an interesting idea for clusters. And in fact, it could be a very educational way to go about building a cluster and teach yourself about cluster computing. So how do we load balance? That's a problem with cluster computing. I want to make sure each one of my little Raspberry Pis gets about the same amount of load. I need benchmarks for my clusters. I don't really know what is the correct benchmark. It depends what you want to do, really. I need a mechanism to register the volunteers on my cluster. I have to configure every single machine with some kind of compute server so that I can dispatch jobs to the different machines. And I have to find a way to detect when they are idle. And certainly computers can report when they're idle. I mean, that's not a big deal. And you just need a lookup server for them to report to. I have to this is a big problem. I have to take a sequential job and I have to partition it amongst the nodes in the cluster. That's not easy. Embarrassingly, parallel computing systems can do it with relative ease, such as crypto coin mining. That's okay. I can partition that. Everybody gets a different hash problem to solve. That's easy. If I'm Disney and I'm making a big movie, everybody can have a different image to render. That's fine. That's easy. If I'm doing image processing, everybody can have a different section of the image to render. That's an embarrassingly parallel problem. But if I'm trying to do something that's not normally partitioned into a parallel program, I might need to develop a new algorithm to make it parallelizable. And that is not easy. And you can't rely upon your compiler to do that for you. So that's a big problem. Whoops, what happened here? Here's another problem, another cluster problem. I have to find a way to transfer jobs from one machine to another. As a machine becomes available, I have to dispatch another job to that machine. If I know the nature of the job, and I've already created a mechanism for partitioning, maybe that problem has already been solved, but otherwise I need to figure it out. And then I need to know how to run the program on demand. And I've created a system using Java Web Start, which has since been deprecated, that enables you to do just that. And what I can do is I can give you a quick rundown of how that works, just because it's sort of interesting. So here's a Web Start application. And what I've done, let's say you want to deploy this benchmark. It measures dry stones, which is a common benchmark. You can hit open, and then what this does is it automatically launches within the browser, asks if you want to run the program. You say okay, and it runs your little benchmark. So this is running a first-class application on demand. And in the background, he tells you what the version of the web start is and which Java runtime environment is going, and sort of all these different interesting and wonderful things that are happening kind of in the background. The goal is to obtain automatic deployment. I want to quit out of this. Quit. Thank you. There's another example. This is called the Remote Job Submission System using CentAJ. And what this does is it launches a lookup server. Then it runs a test where you have fractals being computed at high resolution across different different compute services. And then we have screensavers that run, which enable us to volunteer the computer into the network. This technology is not like a cluster because the machines are not tightly connected. It isn't virtual machine deployment. It's actually quite distributed, and you can run this on heterogeneous machines. So we don't call that cluster computing. Instead, we call that grid computing. And so what's going on that makes it different is that the grid computers are heterogeneous, they're widely distributed. Their goal is to reach some common compute goal, whatever that may be. And as you can see, volunteer computing, that's when you are running your screensaver. That must mean you're idle. Somebody went to lunch, or they went home, or COVID happened and they abandoned their computer on their desktop for a few months. And so you can sit there and run SETI at home or Boink and effectively solve big problems with lots of little computers. You get the same problems, though. I have to partition my problem into something that's parallelizable. I have to try to transfer the jobs to the different machines. I have to deal with the configuration issues, which is to say, some machines may have different resources than others. One machine might have a graphics card, another machine does not, things like this. So there's all kinds of, does it have enough RAM? Is there, enough CPU time available? Is it even fast enough to make it worth my while? All big problems with heterogeneous computing. Heterogeneous means not like the other, whereas homogeneous means they're all kind of identical. So when you look at something like this, it's pretty clear these are homogeneous computers, right? They're all alike. And they're all geographically co-located, and you can make them into a virtual machine without too much bother. And there's even software like Beowulf, which will run on them. But if I have a network of workstations, whether they all be at Fairfield University or all over the planet, that's not exactly the same thing as cluster computing. That's more like grid computing. And so that's the distributed notion where you don't have a single virtual supercomputer. And so when we look at sort of like the 7 layers, physical layer, data link layer, network layer, transport layer, session layer, presentation, and then application layer, you think, why would I bother with something as trivial as data link layer? And isn't it funny that we're just trying to work through that right now in our microcontrollers class? We're running the so-called NRF24L01s to transmit and receive packets of data. And what we'll do, and this is sort of an interesting thing that's going on. I'm going to close some of these popping up windows here. There we go. Is there's the send and receive program. You'll be taking a little data structure, which is relatively small, this package, and you'll be transferring it to another machine without any acknowledgement. That's a point-to-point protocol transmission of a packet of data. And as it moves from one machine to another machine, it can move over great distance. In fact, with a Yagi antenna using the same radios that I'm playing with now, One fellow claims that he can reliably transmit over 16 kilometers. And this is an unlicensed radio, right? You don't need a license for it. Power is relatively small. It's running at 2 gigahertz. It's a focused antenna. It's a Yagi antenna. And so I've been playing around with these radios and experimenting with getting them to transmit over distance. And they are not reliable, right? They send a packet. Maybe it got there, maybe it didn't. The transmitter has no idea. The receiver may or may not be keeping track. In this case, it's not. It just prints out whatever it gets. And if it doesn't get it, it doesn't print it. And that's it. And it drops the packet on the ground. That is a classic data link layer transmission. The radio is running in the physical layer. The fact that you're only getting a single packet of data and then printing it if you get it means that the sender has no idea if what was sent was ever received. That is very typical for a user datagram protocol, which actually is higher than the data link layer because it enables networking. See, if you're in UDP, IP, you can actually do this idea of dropping a packet onto the network without having to worry about routing, because routing is taken care of for you by the network layer, the internet protocol. That'll get you out of the local area network. But what I'm doing with these little radios is I'm transmitting and receiving over long distances, and I can go at relatively high speed, or megabit per second speed. And that's kind of an interesting idea. I think we can go up to 2 megabits per second. Although the question of how reliable it is, that's another matter. So then if you wanted to do something to make things reliable, that is, establish a bit pipe, then you use TCP. That's that transmission control protocol. And that's cool because what that does is it enables you to engage in what's known as a unicast IP protocol. Unicast means you identify a specific server, you open up an IP address to the server, and you conduct digital data transmissions to and from that server. UDP is interesting too, but for a different reason. Now I can broadcast packets to the network and they can be seen by many. So I can have what's called multicast. If we go back here, there's nothing to stop all the receivers that are within range from seeing the RF send unit's transmissions. So I've set this up with 10, 20, 30 receivers. They can all see everything being transmitted. And that's really very good because you don't need to establish a connection between the transmitter and the receiver. That connectionless protocol is ideal for broadcast. It's ideal because what happens if you had to do unicast is you'd have to duplicate the stream for every receiver. But you don't want to do that because that's going to waste a whole bunch of network bandwidth, especially if that stream contains audio or streaming multimedia like video. You don't want to do that for every receiver. You want to actually just broadcast it and have everybody receive it. And then radios are perfect for that sort of application because radios don't actually load down the channel any when you add receivers. In fact, you can have 100 receivers and it will take no more power from your transmitter than if you had just one receiver. And so this is a kind of an interesting trade-off, right? A connectionless protocol means you can do broadcast. And that's a big win. So UDP is connectionless. TCP requires a connection. There's a session layer, which enables us to do things like logging in. And then on top of that, we throw a presentation layer like Hypertext Transfer Protocol or Internet Inter-Orb Protocol or Common Object Resource Broker Administration or CORBA protocol or Remote Method Invocation Protocol. That's very Java oriented. Or DBNet protocol, that's database oriented. And, all these protocols, lots of protocols, no shortage. You can create your own even. And then on top of that, you throw in an application. So let's have an example. I'll hop on to my little Java web server over here. And let's take a look at this interesting and wonderful web server. We've got a main method right in through here, and he has created an instance of a thread. And that thread does not run until we hit start. And when we hit start, it becomes ready to run, but it's still not running. And according to this, we have a local variable called the port 8078, which is probably not used by anything else. And we pass it into our instance of a web server. The web server comes in, and what he does is he creates what's called a server socket. And the server socket listens on this port. So here we need two things to connect. We need an IP address, and we need to know the port number. And that'll gain us access to this very interesting web server that we're constructing. What we'll do is we'll run this infinite loop that says start client, and it will not invoke the start client method until server socket accept returns. Server socket accept will block until somebody tries to connect, and then it will return, start a client, and then start another client, all within these threads. So then when it starts the client, it starts the so-called client thread, and the client thread has to do something. And when we take a look, it takes the socket, which is the TCP IP, input and output stream, and it manages it. One thing it does to manage it is it reads what's coming in. So it goes socket.getInputStream, makes a little reader out of it, throws it into a buffered reader, which allows us to do a read line, getting one line at a time. And then we create what's called a print writer for the socket output stream. So sockets have both input and output. And auto flush is true because every time we call print line, we want this to actually send the characters. So when we run, we're going to go through and do a buffered reader read line, get an entire string, tokenize the string using a so-called string tokenizer, and then print it out, figure out what's there. And then if the token equals get, it's going to get whatever comes after get as a file. And otherwise, it's just going to say file not found. And let's see, here's get image, where it'll get an image from the location in a root directory. Here it says count to 10. We could have it do that if you like. Here we have get a file. We're building a little file server, so it has to know how to dispatch different things we might like to do. Let's see if we can run this little web server here. So this is web server experiment number 1. I don't know if we're running this or now or not. If we are, it's going to give us a port in use exception at runtime. I might have been running it earlier. Nope, it's not. So I got to go to port 8078 in my browser. Let's try this with a new browser. And we'll go to localhost, that'll be my IP address, :8078, enter, and then we see, aha, he's giving me some kind of information here. All right, so I built my own little web server, and that's fun. I like that. And we can change how that behaves if we like. Let's close this off. And then that's socket programming. That's the whole thing. There's a lot more to it if you want to get into it a little bit. But you want to build your own web server, you can do it. And this is kind of interesting. You can build a web server in on a little Arduino Uno and make it into a web-based networked embedded system, which in principle could do things like run a robot, serve weather station information, control a mill, whatever you like. So it's kind of an interesting idea. You can use the network as a substrate, which gives you a clean interface from high-level languages like Java or Python or whatever you like, and then proceed to effect control at a relatively low level with the microcontroller. So that's kind of a neat thing. You could use that for senior projects. So any questions about that? That was my quick demo. We would do a course called, and I do this next semester. It's called network programming. And if you want to get into it, we'll do a little TCP/IP programming. We'll do some remote method invocation programming, and you'll learn how to build your own web server and do all kinds of interesting, fun things like that. Just kind of neat. So what's a domain? This is an interesting idea, right? Well, it depends, right? You have .java, that's a domain, but then there's .com. Now that's what's called a top level domain. There's a top level domain, or TLD. There are many of them, but usually you have one for every country. So if you are in Taiwan, .tw is a top level domain. If you're in China, .cn is a top level domain. And if you're a government agency, .gov. Right? So there's a lot of these, and we're used to seeing .edu and .com, but there's a lot more to it than that. They're all top level domains. And your domain name server, that's another distributed computing system, is going to map the domain names to IP addresses. And I think people don't run these operating systems anymore. But if you notice, they changed the location of the hosts as a function of time. And nowadays, I think they're all in C:\Windows System 32 drivers etc hosts. Whereas if you go into a Unix system, you'll probably find everybody uses etc services or hosts for their hosts. So host list is usually an etc hosts. So here's etc hosts for Mac and Unix systems. That's typical. And normally you put in some kind of a short name so that you can just ping it, right? You know, pinging it. Like I should be able to ping my router. But if I go and look at my hosts, I can see my router has a short name, but it's really router.docjava.com. And if I wanted to, I could probably ping that. And that would give me the same result. So when we think about socket programming, we think about using the Internet Protocol layer, that network layer, in order to handle the routing for us. And our goal is to move bytes, unformatted sequences of bytes, from one place to another. And in fact, when we think about a stream is defined as an unformatted sequence of bytes. And that's it. So when I send you 4 bytes, what does that represent? And the answer is, I don't know. Why? Because it could be an int, could be a float, it could be a string, it could be anything. You don't know. It could be part of a data structure. So unless you know what the format is of the stream coming in, TCP/IP cannot help you. And that's a problem, right? So that means you have to do something on top of TCP/IP to give that stream some kind of semantic meaning. The compiler doesn't care that you're reading bytes. It'll compile it all day long. It'll read bytes all day long. It doesn't care. What it doesn't do is it doesn't inform you what's inside of the stream. That's up to you to figure out. That's not the function of this layer. So why do I need this socket programming? Well, like you see building a web server, or you want to do remote method invocation or distributed computing or any kind of concurrent computing or network computing. All these different, I'll just say network programming. You can't do network. Well, can you? Yes, I guess. But normally people use sockets to do network programming. Normally. Clearly, you could build a network using your own layers, right? Like these guys, a little RF transmitter, a little RF receiver, easily can build their own network. We don't need TCP/IP for that. We don't. I mean, we just do the reliability checks and the packet checks at the application layer. Cut out all that intermediate stuff. And that might be okay for, a little 8-bit toaster controller with a very specific application. So, for example, if you said to me, well, I want to build a walkie-talkie, and the only thing I'm going to do is I'm going to send little packets that consist of audio, and I'll digitize them and send them as fast as I can, and the receiver is just going to just receive them. I'm going to build a wireless microphone, digital, goes, I don't know, a kilometer with an external antenna. You can do that. People have done that before. And then you'll know what the data is going in, what the data is coming out, and you'll know the range. And, maybe you get a product out of it. I don't know. So that's kind of interesting. Ports. What do I need the ports for? Well, one thing we noticed when we were developing our little web server is it started with a port. So every time we have an application that's going to do a server sockets take as an argument the port. So I need that. Server sockets listen to this port. They accept connections on that port. And you have to know that that port is there, and you have to know what that port is doing, right? I mean, one could make a compelling argument. No one will find this web server on port 8078 unless they scan all the ports with a port scanner and find out there is a port there ready to accept a connection. And if you find that port, you still don't know what it does. You don't know if it's domain host control port or if it's a FTP port, or this is not a standard port number because I just made it up. And I started on a number that was way higher than the normal numbers that you'd see under services. Let's take a look. The last number in my services directory is 49,151. Oh, that's a pretty big number, actually. Let's see what we have in terms of 80. I just grepped on 80 to see if there was an 80. Oh, it was 8078. Yeah, that's not assigned. So there, specifically said unassigned. That was a good choice. Better lucky than smart. So 8078 is unassigned. Therefore, nobody else is taking it, and probably safe for me to use it. I could have selected a much higher port number, but that's the one I took. Good deal. I'll just make a note. Normally unassigned. Of course, if I assign it, then it's going to conflict with anybody else who starts to listen at that port. Right? It's a consumed resource. So let's see now. Here's my example. The server socket is listening on port 1234. Doesn't accept, which will block the main thread of execution. This left-hand side will not return until the right-hand side gets a connection. And then once it does return, we'll get the output stream. We'll get some sort of formatted output stream so we can send a string. This is some sort of Unicode. And then we'll close the output stream. And I don't know what this does. What does this do? It prints hi there on the screen. That's what it does. Not particularly exciting, but that's a server. In fact, you could say it's sort of a text server of some sort. Here's a socket connection made to a server. Notice it needs an IP address or a fully qualified domain name. like show.docjava.com or something like this. And then it needs to know the port number. Once it gets a handle on the socket, it gets the input stream. It can read from the input stream, print whatever is being returned, and then close everything up. That's client programming. That's it. Now, if you wanted to do something where you're actually getting some kind of remote method invocation, well, that's different. Right now, you're talking about sending jobs to another machine so that the other machine will execute the job. So now I want a format where the computation server is able to do some kind of computation. And I have to know what the handle is on that. And what is the return? What do I do to compute something? Stuff like this. Any questions about what I'm covering? You guys are very quiet. We have a reasonably good showing here in the class. Am I going too fast on this? There's a button that says go slower or go faster, so you can use it if you like. Well, I guess I'll just keep going. So then there's this idea of multicasting, and we discussed that already. These NRF24L01s, I'm going to show you one just so you can see it. It's not good to talk about these things in the abstract. NRF24L01. There they are. That's a little radio. $1.70 for a radio. Can you believe it? Mass produced with an antenna and an SMA connector covered in gold. Yes, it's real gold. It's a very, very thin coating. It's got a little NRF24L01 chip that you can't see here. Can you see it here? You can sort of see it. There it is. This over here, that's a low noise amplifier and a programmable gain power amplifier. Actually, this is the NRF24L01. That's the amplifier right over in there. And then that goes straight into the SMA connector. And this can be used as both a transmitter and a receiver. It is a transceiver. And I think we can find a nice video of it being used. I believe that's worth watching. Just a minute here. Microprocessors. You know, with regard to digital data communication systems, it's worth looking and seeing just how these things work. It's kind of cool. And I don't know if you can hear it. Let's see if I can make it full screen. So there it is within a little adapter that comes in. That's got a. You know what I'm going to do is I'm going to turn my volume down. I'll do my own narration because I know what I said. So this here is what's called a Pro Micro, which is just like an Arduino Uno, only smaller and cheaper. And it's hooked up to the NRF24L01 using a bus known as SPI bus. That's a serial programmable interface bus. And so that has a master out slave in called MOSI and a master in slave out called MISO. It's got a little voltage regulator and a bank of capacitors in through here. This is a picture of it. It's not the actual thing, but it's easier to see the little parts. And here's the actual thing sitting on an Arduino shield, transmitting data from one place to another. The goal on this one is to try and measure the fluid level in an oil tank and then transmit it. There's a supercapacitor in here for storing data, so it wakes up once every week, measures the distance to the oil. And so here's an example of the transmitter and receiver acknowledging and transmitting data back and forth with respect to one another. And so if you have something like this, then what you've done is you've imposed a little order onto the data link layer. And that enables you to effectively validate the data has been actually sent and received. So that's one way in which you can control, well, one way in which you can do digital data transmission. Here's another one. This one is called Bluetooth, which is common. This is another Pro Micro, and this is a Bluetooth module off to the side. What I'll do here is I'll get this to play. So Bluetooth is interesting because there's a lot of computers that have Bluetooth built in. This one is Bluetooth 2.0. I found out that Bluetooth 2.0 does not work with my iPhone because somewhere around iPhone 5 or 6, they decided they were going to only use Bluetooth BLE or 3.0 or better. And so I've got to upgrade my little Bluetooth transceiver. But only thing Bluetooth gives you is an RF link for what essentially looks like a serial port. You can simulate different protocols with Bluetooth. You can use HID protocol, for example, and simulate a keyboard and a mouse. You can, what else can you do? Oh, I don't know. You can simulate a USB thumb drive with one of the protocols. In this case, what we're doing is we're using a program called Circuit IO, and we're dropping in our little Bluetooth module into our Arduino Micro schematic. And then what that does, and this is kind of cool, is it not only gives you what the wiring diagram should look like for the two different modules, which greatly speeds prototyping, but it also enables you to see the, let's make it full screen again, sorry about that, to see the code. So the sample code can be obtained if you click on the code tab, and that kind of makes it nice. And if you want to swap out an Arduino Micro for an Arduino Uno, you can certainly do that. In fact, there's a little single chip version of the Arduino called the AT Tiny, which I think is 50 cents or something like this. And that's really good for an embedded project. So there you can see how we quickly swapped out the Arduino Pro Micro for the Arduino Uno and used the same exact peripheral, the Bluetooth interface, which is pretty cool. And he gives you the code for attempting to do the transmission and reception. And if I'm right, I think we can speed through this quickly, and we've made a little chat program out of it. And so now you can see what's coming out from the Arduino after Bluetooth has connected. So this is a connection to the HC05 Bluetooth peripheral using the radio at 9600 baud. And over here is the Arduino taking in some text, building a little chat program here. And when I hit enter, it should output through the RF interface, and it comes out and says, hey, this is the Arduino monitor. We're here. And now I can go back to the Arduino and I can input some text. And as I type it, it comes out in real time onto the our Arduino's monitor. So the transmit receive is sort of validated in this way. It's not going particularly far, and it's working with a Mac because iPhones just don't work with Bluetooth 2.0. What can I say? At least not the new ones. I could probably try it on an old one, but what's the point? Time to upgrade. And so you can see the HC05 when you scan for Bluetooth devices. And when you click on an HC05, I think the prototypical password for something like this is 1234. So it needs to pair. So you pair it first. It establishes the device as a Bluetooth device known to your computer. You do your connection. And guess what? This is point-to-point protocol. This is a data link layer protocol. No routing. Looks just like a serial port from the operating system point of view. It's just a serial port that happens to have an RF physical layer, and that's Bluetooth. So that's a pretty cool way to go about describing data link layer and why it's important. So we've seen two examples now. We've got the NRF24L01, which can go a kilometer. We've got Bluetooth, which is good for no more than 10 meters, at least Bluetooth 2.0. And in case you're wondering, 10 meters is like 33 feet. And only if you're not in the way, and only if there's nothing else in the way. That's free airspace, right? That's best case scenario, 33 feet. So that's Blue Chat. Blue Chat. What do you think of that? Blue Chat. So that's let me see if there's any other good examples. Yeah, there's a Wi-Fi example down in here. We can see this one too. So now we're going to go into a little bit of a higher layer. This is with an embedded microcontroller I've been mucking about with called the ESP8266. Now what this one does is it includes a 32-bit machine, which is quite a bit nicer than the Arduino for sure. And what we'll do is we'll run a web server on the 8266. And what it does is it gives us an access point. And here is the 8266, and we're going to configure it so that it can find the Wi-Fi in the house. So what I do is I go in and I can find my Wi-Fi network, and there's Netgear, and I can throw in my little password, whatever that is, and then I hit save. That configures it so it can then make a connection. And once it makes a connection, it turns from an access point into a Wi-Fi client. So you don't actually need to have any kind of a console interface in order to gain access to the 8266. Moreover, if you wanted to use an iPhone, you could find this as an access point on your iPhone and configure the client directly. And what it then does is it gives you access to a load cell, which measures the weight of the water in a dog bowl. Why would anybody want to do that, you ask? And the answer is because we wanted the Internet of dog bowls. Don't laugh, it's a thing. So yeah, Internet of dog bowls, because, and also cats, because when they have kidney diseases, we have to monitor how much water they're drinking. And so what we do is we instrument the water bowl to see how much water they're drinking, and we can report it and graph it on our little iPhone apps. Internet of dog bowls. In fact, if you think about it, when you take a course like the microcontrollers course, you're basically learning how to interface everything to everything. And isn't that what the Internet of Things is really all about? Interfacing everything with everything. So that's that. So you've got your choices of ways in which you can connect. If you're doing the Wi-Fi thing, you're actually in the network layer now. And you can see many different Wi-Fi services were available because I'm in a complex that has many units, and they're all password protected. So you've got to configure your Wi-Fi based devices with a password, and configuration is the challenge for the Internet of Things. You have to have everything configured properly and secure. It's not good enough to just have a password like 1234. That's no good. If you're multicasting through a network, you want to get beyond your local area network. You want to go from one router to the other router. And then you could say, but that doesn't sound good, right? Because if I have multicast packets that can jump from one router to another, why wouldn't they just flood the entire internet? And in fact, they would. However, not every router is capable or willing to route multicast packets. Moreover, every multicast packet has a TTL, or time to live. and that is the number of router hops before the packet is blocked. And that is usually limited to 3 to 6, and then it stops. So if what you're trying to do is make a broadcast mirror inside of a local area network, you can have that broadcast mirror issue streams using multicast, and then you can get to it using unicast. So you can go behind the firewall, get to your broadcast mirror, and then effectively create a multicast backbone or M-bone for all of the other clients to latch onto. That way you don't have to duplicate streams as you go from one workstation to the next. So this is that's a way around the fact that some routers are not going to let multicast packets in, and certainly in an industrial setting, they would not necessarily, in fact, almost certainly would not let multicast packets in. So then here comes this class called the INET address. And that's interesting to us because you need an internet address in order to be able to start to get something like a socket. I need a port and I need an internet address. So they've encapsulated the internet address in the INET address class, which is in the java.net package. And so I can get a host's address by name. I can get the internet address. I can get the local host. These are sort of interesting things you want to be able to do with an internet address. So here's a class called host info, and it looks to me like he gets the local host and figures out what the IP address is. I'm not going to run it because it's not particularly interesting unless you want to see it run. Anybody want to see it run? You can hit me up on the chat if you want. No? Okay. We won't do that. And then here's something that's going to resolve a name and turn it into an actual IP address, the resolver. And I have these already coded up in a little network package. And so there's a whole host of different utilities for doing these sorts of things. I have examples for doing remote files, RMI, secure copy, all kinds of interesting server examples. The port scanner, which I think we saw the other day, a mail server, a Kickstarter miner, Dropbox interface. A lot of people like using Dropbox. A DHCP client, time and date service and client. Too many services to run through, really. Too much to do. You can do that in a networks class. I think that's where it's best done. So then here's the resolver. He's going to just make use of that INET address. And here's the daytime services. And I think we might have seen this before. I don't know if that server's still up, but you can certainly try it. Yeah, he's down. So there's got to be a time server available that's up. Probably NIST has a time server. Oh, they're phasing it out. Ah, geez. Well, I'm not going to read about how they're phasing it out. That's a shame. That's too bad. To get my daytime services elsewhere. I created my own little Java daytime server, and that's using the time of the computer, and the computer's getting its time over the local area network as well. So at some level, you can make a compelling argument that you have a good crystal in the CPU already, it should be able to keep time, but it has to be able to figure out how to initialize itself and how to reset itself whenever the time gets out of skew. And so it has to go somewhere to get that information, whether it's through the network or through some sort of radio broadcast technique like CHU Canada will broadcast. I don't know if you guys are familiar with this. It might be educational to see it. So let's just take a quick look. If you go to, I think it's called Canadiano, CHU Canada. There it is. So that's a shortwave AM transmission of the atomic clock coming out of Canada. So you can get a product like, I don't know, Amazon has an Arduino clock that'll go to CHU Canada. I don't think it's terribly expensive. These are little crystal clocks, but they have to be set initially, right? You have to initialize them. You have to set the clock. And they've got a little 32,768 hertz crystal on the side, just like your watch, and they'll give the Arduino the time. But to set the time initially, what you want to do is find some sort of a source, a good source. And so what you'll do is you'll get, I think it's called Canadino or something like this. Oh, it's a shield. I know what to do. I'll just type in shield. And somewhere in here, it comes. You'll see it. It's got an AM shield, AM radio built in, and it's not the correct way to search for things. I'll find it later. Don't worry. And effectively, it lets you. Actually, I know where to find it. This is it. That's it. So this is a little bar antenna off to the side that hooks into the little antenna interface that you can see over in here. And what it does is it picks up, it is Canadino. It's a strange name, isn't it? And it will receive the atomic clock over the broadcast to resynchronize the clock without a network interface. And that little can over in there on the left, that's a 32,768 hertz crystal. And they divide that down because it's an integral power of 2 in order to be able to get a single pulse every second. And let's see, WWVB is the call letters for CHU Canada. So they can basically keep you synchronized with the accuracy of an atomic clock. And the reason you don't just use these little crystal clocks and forget about everything else is you're losing 2 seconds per day, especially if we don't know the quality of the crystal and capacitor matches, or if there's drift on temperature. And sometimes that's okay, but some people find that an unacceptable thing. So getting CHU Canada lets you resynchronize once a day or more if you like, and that can be to your advantage. I think there's a picture. Yep, there it is. This is a typical real-time clock module. We use these in the lab, and it's a pretty trivial thing to do. In terms of the code, it's already been written and supported. So you just plug this into the Arduino and set the clock and off you go. But if you want to set the clock automatically, then you probably either want a network connection or something like this. I guess that's not too much money for an extra shield and a radio. does something special like that and gives you the accuracy of an atomic clock. I guess that's okay. So here's the daytime client, and what he's doing is he's opening up a socket using the daytime port, which is port 13. And so he then proceeds to read in what's returned, and that's a string that's supposed to have the time on it. And you can get that from most clock servers. So the socket needs an address, an internet address, and the port. And it's typical that you can set something like the timeout in case, I don't know, things on the network are generally not reliable. And then here's the server socket. So that's the other side. That's the part that listens for whatever it is you're doing when you do a connection. And so when we do an accept, it stops the main thread of execution and waits for someone to come in and do a connect. That's why we always launch a thread to invoke the accept. And so here's a time and date server. And now this is a little bit different from the web server that we saw from before. Now what he's doing is he's waiting for that accept. Then he goes and he creates a string from the client and prints it out. Then he creates a print writer from the output stream that the client has created. So he's going to write directly to the socket. And notice when he says true over in here, it automatically flushes. And then he says out.print today. And so he's going to take a string representation of the date, today's date, and then he's closing his socket connection. And that's his daytime server written in Java. And here's the daytime server in action. The Kiev guys are down for whatever reason. And so that's your intro to socket programming, distributed computing. How exciting, right? That's good. Sort of get into it. If I wanted to, I could talk a little bit more about how multi-threaded servers work. And that's actually a reasonable thing to do because we've seen threads in a few different ways. They're low overhead context switches, which are used primarily to enable a kind of simulation of concurrent computing. The threads do not do two things at the same time, but they simulate it, particularly in the Java virtual machine. Now, that might be a little bit different when you do hyperthreading, but then you're only getting 2 threads per core, and hyperthreading is actually a proprietary Intel name. So that's a Java view of multi-threaded systems. So you're going to have one Java virtual machine. For example, here is a Java virtual machine. Now, it has running in it a thread that runs this clock. But it also has another thread that runs an address book. And if you want to do something that blocks the primary thread of execution, you might try to dial the phone. I don't really want to bother the secretary by dialing the secretary. So let's try and dial information or something like this. And so then that's blocked the primary thread of execution. Now I can hang up. That was a modal dialog box, right? I can't do anything here. So I hit hang up, yes. And presumably that information person didn't have a chance to answer because I didn't let it ring. And so what it's doing is it's making a connection using the serial port, right? This is point-to-point protocol. And that serial port has, well, I don't actually have a COM port or an actual serial port. What I have is a USB interfaced serial port, but it thinks it's a serial port, so it has to be set up with a baud rate, a number of data bits, parity, number of stop bits, and flow control. And you can always test the port. And then there's another thing you can do where you do your dial setup, and you can choose how fast you dial and whether you use the speaker or touchtone or the modem. And once you set that up, it'll retain those settings. And all of that's happening while this thread is running in the background, counting the time. Multi-threaded programming is kind of important for us because we need to be able to do multiple things at the same time. And it's all happening within this single task. And you can see all the different things that are going on. Let's see, show all windows. It's coming up in a different monitor, so it won't do anything. So the multi-threaded servers, that's kind of the way to go. You can have many thousands of threads. A little machine like mine could easily run 7,000 threads, no problem, as long as they don't need too much computation. And so if I'm going to wait for an accept, I'll put that in a thread. Every time somebody makes a connection, I'll manage that connection in another thread. It's really the only way to go. Multicast sockets, they're broadcast sockets. And if they have a time to live that's non-trivial, like 3 or 4 hops, they'll be able to go from router to router. And as you proceed to send out these packets, you can send out each one with a separate thread. So you don't actually need to hear back from clients. In fact, you probably won't. You'll just be pushing multicast sockets out, multicast packets out, and someone will be receiving them. You could have as many as you like. It won't increase the load on the network. Just like broadcasting to a bunch of radios. You know, it doesn't matter how many radios are listening. It doesn't use up any more bandwidth. But like I said before, nobody requires your router to pass multicast packets. That should say packets. And somebody, well, I guess the same thing as saying multicast may not be supported on your network. So that's no difference. Time to limit, that's the limit to the packet spread and equals the number of routers, which is the same thing. And applications, I've been thinking of them, you know, the lookup server idea, where you have a bunch of compute clients that wake up and they need to see if there's anybody out there managing them. That's one way to go. Plug and play printer. You know, some people call these zero network administration devices. That's a good application for multicast. It's good for discovery, like, for example, where is my domain host control protocol server? I want an IP address. Somebody give me an IP address, right? So you come up to the student network on Wi-Fi with your iPhone and you want to get on that network, you need an IP address. The DHCP server will give that to you. Unicast is good for correspondence. It's a point-to-point protocol. An ether switch does a sort of routing that protects network legs from traffic. So if the ether switch is a piece of hardware that kind of decides which way the networks are going, it's kind of like the traffic cop. And it says, okay, you go this way, the other one goes the other way. It does a kind of routing. So ether switch is interesting because unlike a router, it will pass all the multicast traffic through. It only isolates unicast traffic. And you can get these things out to, well, last time I checked was 10 gigabits per second. My ether switches are running at about 1 gigabit per second. I don't think I need to go to 10 gigabits per second yet. My computers can't handle that, but that'll be next. And now we can do video on the Ethernet. And we know about this because Netflix, Amazon Prime, and the cutting of the cable, all because we have faster networking. That's an enabling technology. In fact, if it wasn't for faster networking, we might not be able to have the kind of online shopping experiences that we have. Oops, what did I just do? Okay. So broadcast video is an interesting thing because it has changed over time, but the original CCIR 601 standard, which you grew up with, was not an HD TV standard. It was like 720 by 480 pixels. There were 16 bits per pixel element at 30 frames per second. Uncompressed, you were running 160 megabits per second. But you know what? If you've got a 1 gigabit per second network, I suppose that's okay. So here in the new age, HDTV is part of what's known as the Grand Alliance. And the HDTV Grand Alliance is 787p, 1125i, and 1050p, I think, are the different formats. And most TVs can handle all of them. I don't know if I have those numbers right. I'll just put a little question mark there. I got to look that one up. It's been a while. So what about video? What is that? And I say, from the multimedia point of view, it is a sequence of images with synchronized audio. And a sequence of images, I don't know, how do you make that? Well, you can use a camera, or you can use a computer to synthesize the images one at a time. If I use screen captures like you're seeing here, where I'm actually capturing a PowerPoint presentation without a head and shoulders shot, it seems to me like the compression algorithm ought to be able to take advantage of the interframe coherence and the intra-frame coherence. All right, so intra-frame and within the frame. And so if I know that there are these large areas that are essentially constant color, I can code them very efficiently. And then I can use a code book. And code books will take large areas like this and just code them as large rectangle, all the same color, and transmit the colors. And this color scheme, that it's a black and white thing. I mean, maybe some large blocks of color, relatively easy to code. And so then there are these libraries. And it's really, I guess the way you would term it is java.net framework, right? It's a framework because it's not really anything other than a collection of classes and tools that effectively allow you to do things like network programming. And so we've already discussed multicast sockets and server sockets, regular sockets. Regular sockets make connections to server sockets. Multicast sockets allow us to transmit broadcast. We've talked a little bit about the Ethernet address. Datagram packets and sockets are for specialized UDP transmissions. And URL, I think we know what that is, but there's a class called URL. And when we go to the URL, we can get a URL connection, and we can set the URL connection properties. So give you an example of that real quick. There's a network.url utils. URL utils has, let's see if we can find that real quick. Yeah, it's in net.web. So it should be possible for us to look at some of these things. And like, here's get URL connection. So we pass in a string, which could be, I don't know, http://www.docjava.com, make an instance of a URL, and then go and get the URL connection. Then tell the URL connection, well, hey, we're a Mozilla browser. And that might be really useful. And we'll set the read timeout and the connection timeout, and then return the URL connection to someone who might be interested in creating a socket from it and listening to the data. So that's kind of interesting, and we can do examples of that kind of programming later. But I just thought you might like to see some sort of real network programming. So that's what we have time for today. Here's my multi-threaded clock. And I want to thank you very much for your attention. Stay safe. You've got a homework due on Thursday. Take care.
Thank
Good day,
you.
Professor. Thank you.
Thank you.
Thank you.